Okay, thank you very much. I will tell you a little bit about a few new things that we've been doing on nonlinear scales of cold dark matter and trying to test, of course, the prevailing paradigm. Let me just start with a few words here to set the stage. As you know, we measure the structure of the universe on many different scales. And what we found over the past, 20, 30, 40 years, so the structure of the universe looks more or less like this at the bottom of left of the screen. It looks like a universe that is very highly structured on small scales. In other words, the average over small scales is quite different, of course. If we place a little box of the size of the solar system, will be very different, depends on where you put it. But if you place a box of the size of 100 megaparsecs across, it actually looks very similar regardless of where you put it. So that's the richness of structure and that particular way in which the structure is changes as a function of volume or as a function of mass is of course encapsulated in the mass variance as a function of scale, mass or distance or volume, as you in the x-axis here. And this is one example of what you see when you measure the structure of the universe on very different scales using a variety of probes, from the laminar alpha forest to the microwave background to weak lensing to the ones of clusters, etc. All of those measurements are made at different redshifts, and then they are actually extrapolated to a particular common time in order to be able to compare them. And when you do that, you end up with this very remarkable, dependence on mass, which has, it's a very clear, not a power law. It's just something that bends over in a particular way, and which is exactly very well fitted by the predictions of the cold dark matter paradigm. So that, of course, the success of this theory over 7 decades in variance or over 10 decades in mass is so tells you that something profoundly correct is going on with this paradigm, and where basically the structure is very well understood, and all the parameters are actually quite well specified. Now, one interesting thing about this, if you want to try to extrapolate this paradigm, is, for example, you can go to smaller scales where we have no measurements, below 10 to the 12 or so solar masses, there are no measurements. And the reason why there are no measurements, at least that appear on this particular plot, is that this plot, these measurements are all made on the linear regime. If you look at the left-hand side here, you see the all 10 to minus 6, 10 to minus 4, 10 to minus 2. This is all less than 1. So these are small perturbations. So these are done at different redshifts at different times in the universe, but when those particular scales were still in the linear regime. So the question is, does the cold dark matter both hold on very small scales or also on very nonlinear scales? Once these perturbations go from the linear regime to the nonlinear regime. And that is what I'll try to tell you a bit more today. Of course, in the universe that's only made of cold dark matter, where the initial conditions, as you saw before, are well specified, and linear regime are well specified, you can put this in the computer and solve the equations, and that's what we've been doing for the past several decades with quite good success. So I think we now know, if the universe was made only of cold dark matter, we know the distribution of cold dark matter on all scales that are relevant for the problem very, very well. Okay, there are basically no things that we don't understand here if the universe was only made of cold dark matter. We'll get to complications in a minute that come from the fact that the universe is made also of baryons, like the ones who make our own bodies and our own stars and our own solar system. Okay, but we know basically where to start, and we know how this structure is on very different scales. Now, when people have done this and gone to the very, very nonlinear regime, regions that are very, very high density, in other words, where the crossing time is much shorter than the age of the universe, then some problems or some challenges or some difficulties have arisen, and I'll listed here a few, perhaps the most notable things that people have discussed over the past few years, things like the missing satellites problem, a too big to fail problem, mass discrepancy acceleration. Actually, many of these problems, which 10 years ago would have been still quite salient, now they've been actually resolved. Now we don't think these things are problems anymore, like the missing satellites problem or the mass discrepancy acceleration. Those things are very well understood, I think, within the realm of cold dark matter. Others are less well understood, and because we haven't found any other evidence for dark matter, not just cold dark matter in the laboratory or in direct experiments, at least not convincing ones. Astrophysics, this kind of study that we do, studying galaxies and things like that, is really the only probe that we have into cold dark matter at the moment. The only way we can actually make contact with the predictions of this paradigm. Okay, so we are in that regime. So now let me tell you a little bit about cold dark matter now on very nonlinear scales. What happens when cold dark matter aggregates itself onto very high density objects, very nonlinear objects, where as I said, the crossing time becomes shorter than the age of the universe. Okay, so we call those things, those basic units of the structure of the universe, we call them cold dark matter halos. We know a few things about this. We know the structure fairly well, and we know also their number, their abundance as function of mass. So for the structure, just a couple of words here, and I want to go through a few basic things that you want to keep in mind that'll be useful when I discuss other things in the rest of the talk. So these are two cold dark matter halos. As you can see, the dark matter arranges itself in a way that has a very well-defined center. Here, these are two halos, two very different masses. They've been, of course, so they're very different in size as well, but they've been scaled to have the same size in a particular definition. And the way that we define the size of a halo, that also actually implicitly defines the mass of the halo, is by identifying, walking from the center, which is obvious, outwards, identify the region where the mean interior density is such that it's about a couple hundred times the critical density of the universe. That choice comes from the fact that with that definition, the time it takes to complete a circular orbit at that radius, we call it that the virial radius, is about the age of the universe. So inside this region are things that can't have reached dynamical equilibrium. Outside are regions that are, on average, most of them are still collapsing. For the first time, they haven't yet completed a single orbit within the system. You can see when you scale things that way, this cluster, which is 1,000 times more massive than this one, looks very much alike to the other ones. Actually, every cold dark matter halo looks very much alike. So the similarity is a very profound and powerful tool that we use in order to make predictions for cold dark matter. With this definition, also the mass scales like with the velocity of this putative velocity of a particle in a circular orbit. It scales with an interesting power, which is the cube of the velocity. So we'll get back to that also in a minute. This self-similar nature of cold dark matter, we've of course worked, and I worked on it for quite a while. You can see here, this is the density profile now of 4 different halos of different masses. You can see that can be very well fit by a simple formula, which has 2 scaling parameters. And the formula itself, it doesn't matter very much. What you can see that is that this density seems to, first of all, not have any, seems to have a divergent nature towards the center. In other words, we do higher and higher resolution simulations, the density always keeps climbing up. And the other thing is that it curves over. This is not a power law. It curves over and is shallower than isothermal in the inner regions, like R-1 more or less, and steeper than isothermal in the outer regions, like R-3 or so, in a simple, broken power law fit. So, and also it's the same. This one is the same for all of them. So if you take this low mass here and I shift it down and to the right, I'll match this one, the most massive one exactly. So it's only one parameter aside from the mass that characterizes fully the mass of the mass profile of a cold dark matter halo. You can think of this as the scale radius. Inside the scale radius, the density profile is less than isothermal, it's shallower than isothermal. The velocity, the circular velocities will increase. So this makes, we can plot this in a different way. Instead of plotting the density, we can plot circular velocities, which is we're plotting the putative circular velocity of a test particle going around in a circular orbit. You can see because of the shape of the profile, the shape of the circular velocity goes up and down. Okay? Goes up and down, goes down towards the center, goes up to maximum, and then drops in the other parts. And this will be actually quite important. This prediction that circular velocity rises up to a certain maximum and that maximum occurs at a particular radius that is fixed by the cosmology, it's fixed by the parameters, the Hubble constant, the number of omega matter, the amount of matter in the universe, omega lambda, etc., is actually quite important, because all those parameters are fixed now in our cosmology. We cannot change them anymore. So, for example, for this halo that has this particular velocity, maximum velocity, say 100 kilometers per second, this peaks at 20 kiloparsecs and not at 30. This is not a parameter we can change anymore. This is completely fixed. This is a prediction now of cold dark matter. Okay, remember this velocity rises in the inner regions. Now, the other thing we know is how many of these halos there are. You can plot the abundance of halos function of mass per unit volume. This is this black curve you see over here. Now, this is actually quite different than the abundance of galaxies as function of stellar mass, which is what's plotted here in color. And that tells you that if halos are where galaxies form, which is part of the galaxy formation paradigm, then there must be galaxies and halos must respect the relation between their masses that is quite well specified. And one simple way of understanding that is by perform what people call abundance matching, which just means that we're going to associate the most massive halos with the most massive galaxies in a horizontal way, if you want. So look at this line here. So, for example, 10 to the 12 solar mass galaxies are associated with 10 to the few times 10 to the 14 solar mass halos, because there are as many galaxies per unit volume of that kind as there are halos of this kind. Of course, you can do a matching at all masses, and that gives you a unique relation between halo mass and galaxy mass. The important thing about this is that because of the shape of the galaxy stellar mass function, it becomes very shallow at the faint end, at very small masses. Then imagine this was exactly shallow. Then all of these curves, all of these lines here would correspond to the same halo. In other words, there's a preferred mass scale in the halo mass function below which there are no galaxies. Imagine you have a mass here, 10 to the 9 or something. You see there are so many of them that if I were to do the abundance matching, it would never match anything. So there's like a threshold, a mass in the universe, or a halo mass, below which galaxies don't form. The relation between galaxy mass and halo mass is very nonlinear, and I can show you an example here. There's halo mass in the x-axis, galaxy mass in the y-axis, and you'll see how this curves over. It becomes very steep at the faint end, at the low mass end, just as if it was a threshold below which galaxies don't form. So that's another interesting thing that we know. So what we know is how to associate masses, halo masses and galaxy masses in order to match the stellar mass function, which is an important measure, empirical measure that we have of the universe. Now, of course, simulations have grown, not just simulations only of cold dark matter, but also they include the formation of galaxies and stars, etc. And now we have simulations that actually match this stellar mass function very, very well. Okay, so we have been able to encapsulate not just us, but of course other groups as well, encapsulate the physics of star formation and galaxy formation, at least in parametric or basic ways that allow us to reproduce many of these statistics actually quite well in simulations. So let me start by we'll talk about two things in particular. Talk about scaling laws in cold dark matter, which is something I worked on over the years, and also we'll talk a little bit about rotation curves. And the first, I started talking about galaxy scaling laws. One of the peculiar things about galaxies, again, we're talking now about a very non-linear structure, right? The very inner regions of the dark matter halos. That's where galaxies lie. One of the interesting things is that in astronomy we have basically two different kinds of galaxies. One where the stars all go around around more circular orbits, like these galaxies, like this one I'm showing here on the right, or elliptical galaxies where there's no preferred sense of rotation for the stars. In the case of these galaxies, something was noted early on, in the 70s, was that if the rotation curves are actually relatively flat, as I say, so rotation curves, of course, at 0 near the center go up, and then they stay kind of flat. If they stay kind of flat, of course, is one of the handles that we have about the existence of dark matter halos. But what's interesting is because it's flat, it's easy to associate one number to every galaxy. This galaxy, you have one number, which is the velocity in this flat part. And so it's easy. So every galaxy you can characterize it by stellar mass and velocity. And this, of course, has had some kind of scaling. This is what's called a Thaler-Fisher relation. As the mass increases, the velocity increases. That is more or less like the cube of the velocity. You can see here Luminoso galaxy, so the cube of the velocity, which is reminiscent of the scaling between mass and velocity that I told you for dark matter halos. So that gives you a clue. The other thing that's interesting about this is that you can have this galaxy like this one, or this galaxy that is 10 times larger of the same stellar mass, 10 times larger. And interestingly, it has the same velocity. The velocity doesn't change. This is a characteristic velocity, which is strange, right? Because the virial theorem will tell you that if you take a mass and you change the radius, the velocity should change. Why is it that this doesn't happen? Why is it that there is no radius or surface brightness, as people call it, dependence on the Thaler-Fisher? So that's one thing that's interesting. It's also interesting because when you go to these elliptical galaxies, these other galaxies here, like you can see here, that is not true. For elliptical galaxies, if you have two galaxies of the same stellar mass, but they have two different radii, their characteristic velocities does change. As the galaxy becomes smaller at a fixed mass, its velocities become higher, as you expect, more or less, not exactly, as you expect from the virial theorem. And so where m is sigma squared times r. So if I fix m, if I decrease r, sigma has to increase, right, in order to keep the same mass. So why is it then that in spirals, the radius doesn't matter, and in ellipticals, the radius does matter? It turns out this is a result of this particular structure that I was telling you about, this the particular way in which the dark matter distributes itself around in dark matter halos. Let's give an example here. This rising curve, this red curve, is the circular velocity profile of a cold dark matter halo of about 150 kilometers per second, just as an example. Now we know in that halo what galaxy should live. A galaxy of about 3 times 10 to the 10 solar masses should live in that halo. Now what this abundance matching does not specify what's the radius of this galaxy, how it's small or how big is it. But we can make the assumption that it is a disk galaxy, like an exponential disk, a typical approximation for a disk galaxy, and just give it different sizes. I can have a size of a half mass radius of 30 kiloparsecs, or 20, or 10, etc. And what we can do is now construct the circular velocity profile of that galaxy. If that galaxy is very large, like 30 kilometers per second, you see over here this open circle here, that's a half mass radius, then the contribution of the baryons to the circular velocity is the bottom blue curve here. It's basically irrelevant. So what you're measuring is really just the velocity of the halo. And when you measure the velocity at the half mass radius, you measure the terminal, the flat velocity of the dark matter halo. Now, as you make the same galaxy, if you take another galaxy of the same stellar mass, but smaller, 20 or 12 or 7 kiloparsecs, now the contribution of the baryons becomes more important. But you see the contribution of dark matter in the inner regions is smaller because this is a rising rotation curve. So the two compensate so as to give you the same velocity, the same total velocity at the half mass radius over a very wide range of radii. Galaxies with 4 kiloparsecs of size or 30 kiloparsecs of size give you more or less the same velocity. So all these circles basically align on a horizontal line until you get to a certain radius. Inside a certain radius, that's not true anymore. Inside a certain radius, because the dark matter is rising, inside a certain radius, there is almost no dark matter. And the baryons and the luminous part starts to dominate. You see how the velocity shoots up as the size of a galaxy becomes smaller and smaller and smaller. So in other words, for every galaxy, for every halo mass or every galaxy mass, it's the same because they're matched by abundance matching, there is a critical radius below which the radius of the galaxy matters and above which the radius of the galaxy does not matter in terms of their velocity. And that is exactly what we see. Spiral galaxies, in other words, have velocities independent of mass because they are bigger than a particular radius. And elliptical galaxies are not. Elliptical galaxies, in other words, deviate from the Thaler-Fisher in that sense because they are so small that they dominate by the dark matter. And this actually is perhaps less appreciated than it should be, because this is a non-trivial, it's not a coincidence. This has to be this way. This red curve cannot change I cannot just make this red curve, be a bit flatter or a bit steeper. This is the prediction of cold dark matter for this scale, for this mass. So we can test these things, of course, and I can show you the results. It says the abundance matching results for one particular, for the Eagle simulation, for example. You see that the simulation matches fairly well, the abundance matching prediction. And this is the Talley-Fisher relation, the results. Okay, so the points in color are the observations. In gray, you actually see the simulations, and they're actually in spectacular agreement. Again, there's no room for error here. If the concentration, if the way in which that particular curvature was different, this would not work. Okay? Now we can play the same game. We'll put all the galaxies together, and I told you the radius is the only thing that matters, right? So for large radius, you can see here the velocities are flat. These curves are in color of different stellar mass. So it shouldn't matter. And for small radii, then they start shooting up. And we can actually compare this with simulations. With observations. And we can actually devise even a novel or a new galaxy distance indicator, which is based on this particular prescription. And actually, we've done that in this paper, Ferrero, recently, and actually works quite well. And so that's one basically success of cold dark matter on very nonlinear scales that is perhaps less appreciated than it should be in my mind. Let me tell you.
You have a few minutes plus 10 for questions. Up to you to use it.
Okay, let me walk you briefly on cusp versus core problem. Now, the cusp core problem is something that Kyle Oman will also talk about later on. So basically, it comes up to the fact that there are, for a given mass scale, there's a single prediction for cold dark matter. And this I'm taking this from Kyle's paper. This is a fixed velocity, fixed maximum velocity. You can see that all the gray curves are all the same. Right? All the gray curves are the same. It means that they are basically all the galaxies should have the same rotation curves if they're dark matter dominated. Unfortunately, that does not seem to be the case. When you take 4 galaxies, this of course carefully chosen, of the same velocity, you see they actually have very different rotation curves, and some are actually below this line, so they have less dark matter than they should have according to cold dark matter. Why is this? It's not completely clear, but we know of some things that we can use in order to tell why that is the case. So this is again 4 different galaxies, the same game, same maximum velocity, and be chosen so they're quite different. What we did with Isabel Santos, who's one of my postdocs, is to investigate what's the role of baryons in the shape of rotation curves. And so what we do is basically measure the shape of the rotation curve. See if the shape is very slowly rising, it will give you there's a deficit of dark matter in the center by combining two things. One is the ratio of the maximum velocity to the velocity in the inner regions, and the other one is in the inner regions, what is the role of the baryons? In other words, the velocity of the baryon predicted divided by the velocity observed. Okay, so now in other words, this parameter eta rot, as we call it, measures how rapidly the rotation curve rises. If eta rot is less than 0.6, these are the galaxies that are have the deficit of dark matter compared to cold dark matter. If eta bar is important to the baryons, if it's 1, it means that the baryons are important. So now there are, for this problem, several things have been proposed. 2 of the ones I'll tell you now in the last couple of minutes. One is that these are caused by the formation of the galaxy itself. So you see, we'll put baryons in the center, we can take them out by supernova feedback. And those, I think Arianna will also talk about this a bit more in a few minutes. In this kind of, pulsating galaxy, as the baryons come in and come out, the structure of dark matter can be changed. And what you predict is that, if there are strong outflows, that can evacuate dark matter from the center, lead to a deficit. But in galaxies that where the baryons congregate again at the center, the dark matter cusp can be reformed. So it makes a prediction here that when baryons are important, because they're compressed, the cusp should be reconstructed. In other words, the more important the baryons are in the center, the flatter the rotation curve should be. There's another, of course, interesting possibility, which is that this is a self-interacting dark matter. That this deficit of dark matter at the center is pointing to a different physical process. And self-interacting dark matter is one where it's not called dark matter anymore. And self-interaction leads to the formation of a core in the center and the depression or basically the deficit of dark matter compared to cold dark matter. Again, in this scenario, every halo would have a core, but in some cases the core will disappear because the baryons that come to the center may actually reconstruct the cusp, right, by deepening the potential. But again, makes the same prediction. The bigger eta rod is, the bigger eta bar is. The more baryons you put at the center, more dominant they become, the cuspier the halo or the system becomes. And we can test this. Actually, we can test this by plotting eta rod, eta bar for a sample of galaxies. In dwarf galaxies, which are the red points here, forget about the yellow ones, you can see that unfortunately prediction is exactly the opposite. Instead of eta rod increasing with eta bar, it goes the other way around. In other words, galaxies seem to have a way of this rotation curves where baryons are very, very important. Eta bars are order 1. Those are the ones that have actually the largest cores, the lowest values of eta rod, and the other way around. If baryons are irrelevant, then cusps seem to be preferred. And this is exactly the opposite of what you expect from this. And this is something that still has not been understood. Okay, they can show you here the simulations. This simulation from the Nihal project. They show you again that the rod increases as eta bar increases. This is from a model from LCDM. Again, eta rod increases as eta bar increases, which is the opposite of what you need to explain the phenomenology of rotation curves. Okay, so it's not completely clear how to solve this problem. It's not completely clear whether this is not perhaps due to errors in or uncertainties in the determination of the rotation curves, but it's something that we're still working on. So I'll leave you here my summary, and I apologize for going over a couple of minutes. So thank you very much.
Perfectly on time, Julio. Thank you very, very much for staying within the So Arianna has a question at this point. I think probably it's better if you switch on your microphone and you ask the question directly, Arianna, maybe?
Right. All right. So, yeah, I was writing it down, but it takes forever. Thanks, Julio, for this very nice and interesting talk. So I was going to ask you something. Is that possible that for some of the galaxies do not observe cores, even though they fall into the mass, the simulation to be able to form cores? Is it possible that some of the galaxies are indeed out of equilibrium for some reason, like they're currently merging, or the Starburst galaxy, or there is something that could explain why they show instead a cusp? So,
yeah, I think that's something that Kyle may discuss later on in his talk. There's a possibility that it's not that out of equilibrium. It's just that perhaps the velocity profiles, the cyclical velocity profiles are actually more complicated than we assume them usually to be when we analyze them. So, for example, when we analyze data of rotation curves, we usually make the assumption that this is a circular disk that is inclined or projected onto the sky, and we try to fit the best circular disks that we can in rings to derive the velocity profile of a galaxy. And maybe in doing that, enforcing that, we may be actually hiding a lot of uncertainties. And actually, when you do that, you may incur problems and that are not really telling you about the deficit of dark matter, but just telling you more about the uncertainties in how you go from the data to a prediction that can be compared with simulations. So, but I think Kyle will talk in more detail about that in a few minutes.
Thanks.
Are there any more questions for Julio? If nobody is speaking up, I would like to have. Can you go back to the slide with the Ferraro et al. Reference about the? Yeah, I basically wanted to see the reference because I wanted to retrieve.
Which one? Sorry.
One in which you were talking about spiral versus elliptical and the.
Oh, right. Mm-hmm.
It's above 2 or 3 above this. Sorry, I didn't write down the number of the slide. Here, the previous one.
This one, this is the Tal-Fisher relation, right?
Go down. Yeah.
Yeah, there are two papers with the same first author, Ismael Ferrero, which was a student in Córdoba, and so one about the Tal-Fisher relation that came out in 2017 to 2018, and another one that we just put out on the archive that deals with both spirals and ellipticals at the same time. So this plot here is from the 2018 paper, and this plot that comes next, which compares galaxies, ellipticals, and spirals, is from the newest paper that's on the archive.
The 2020, and then there was a previous sort of rotation curve. If you can go 2 slides back, I think it is. Maybe I got the name wrong.
Yeah, this is Ferrero also, but I think this is 2018.
One more slide back, I think it is. Yeah, this one, exactly.
Yeah, this figure is from the 2020 paper.
Yeah, maybe I will ask you. So I have a question that I will ask you then the reference of this. I have a question that is coming from Gianfranco, and I will read it aloud. What is the status of the theoretical understanding of scale-free NFW-like profiles observed in numerical simulations?
I think we made some progress on that. I mean, the one that I can point you to a paper by Aaron Latlow, which was one of my students many years ago now. And what he was able to demonstrate is that that particular shape that density versus radius, you can write that density versus radius, that NFW profile, if you want, in a different way. Instead of plotting density versus radius, you can plot density versus mass versus enclosed mass. Of course, it's the same information, just density versus, instead of using radius as a parameter, using mass as a parameter. That, of course, will give you a particular shape. What turns out is that that particular shape, rho versus mass, is exactly the same shape as the accretion history of a halo. Okay, in other words, now take a halo as it grows in time, you plot the mass versus, instead of time, you plot versus density, where the density is the density of the universe at a particular time. So you can compare for a halo is rho versus mass profile today, redshift 0, or is rho versus mass, where mass is the growth of the mass of the progenitor, and rho is the density of the universe at the time. And those two curves are exactly parallel. They have the same shape. In other words, the mass accretion history or mass growth of a halo is the NFW profile, written in those terms. And because those two are the same, one predicts the other. And we can use that to predict, for example, the concentration parameters and all those things. So it seems to be, if you want, the NFW profile seems to be a result of a secondary info on the way in which mass gets put together as a function of time during the growth of a halo. That to me is the most compelling, advance that we've made in the past decade or so, in understanding why it has that particular shape and not a different shape, or what doesn't curve faster or not, or why does it have different parameters, and that sets all the parameters. And as far as I can tell, it works actually quite well.
That's really fascinating. It works that way. I have to look into it. Thank you very much, Julio, for the great talk and for answering our questions. I think we're perfectly. Maybe if you want to share the references with us later on, or if you can put the slides later, you can put the slide with references also, and we will be very glad of it.
Yeah, of course.
Thank you very much. Perfectly on time.
Can you see my slides?
I can.
Good. So good morning, everyone, or good afternoon, depending on your time zone. It's a great pleasure to be here. I would like to really thank the organizer for this nice virtual conference. As Fabio said at the beginning in the introduction, it's great to be able to just see each other in these dark times. So my name is Arianna di Cintio. I'm a fellow at the ESC, Astrophysics Institute in the Canary Islands, and I also work at the University of Laguna, also here in Tenerife. And today I'm going to talk about ultra-diffuse galaxies in particular about their formation, scenario, and their dark matter content. Okay, so let me just move this. So as some of you may have heard, or I don't know, so we just tell for everybody to be aware of what we're talking about. Ultra-diffuse galaxies are a new class of galaxies that were first called like this in 2015, when Peter Van Dokkum and collaborators pointed a very powerful telescope at the Coma cluster and discovered about 1,000 very peculiar objects. Peculiar in the sense that they discover galaxies that are at very low luminosity, so the number of stars similar to dwarf galaxies, but the spatial extent of these galaxies was pretty large. So in spatial extent, this galaxy looked a lot like the Milky Way. And when we talk about spatial extent, we talk mostly about the effective radius, which is the radius that encompasses half of the total height of a galaxy. So you can see here what would be an image of an ultra-diffuse galaxy compared with the Andromeda galaxy. This is, of course, a composite image. And over here, compared with a small dwarf galaxy. So essentially, if you have a small number of stars spread over a very large area, then, of course, your galaxy have a very low surface brightness. They're ultra-diffuse and they're difficult to find. So one of the main questions was, are these galaxies only found in clusters? So there was a question back in 2015, and since then, an extremely large number of observational papers have come out from researchers all over the world, and people have found that ultra-diffuse galaxies are found not only in Coma cluster, but also in Virgo, Fornax, in many other low redshift clusters, as well as in groups and in the field, so in isolation. This image that you see over here is an image of a famous ultra-diffuse galaxy called DGSAP-1. Has been found with an amateur telescope just in the outskirts of the Perseus cluster. So it was found in isolation. The other main question that people had is what is the total mass of ultra-diffuse galaxies? We know that the amount of stars is comparable with a dwarf galaxy, but we don't really know what the total mass in their dark matter component is. So there were two possibilities. Either ultra-diffuse galaxies are a bona fide dwarf, which means that they just live into the dark matter halo of a dwarf galaxy, but then we have to understand why they have such a large spatial extent. And the other possibility is that these peculiar galaxies are failed Milky Way. So they have the halo mass of a Milky Way galaxy, but for some reason they've stopped forming stars, and that's why they are so tiny. One of the first attempts to try to understand what's the total mass of this galaxy was done using the Virgo cluster UDG VCC 1287, and it was done actually by a group of people here at the Institute of Astrophysics in the Canaries. It was done by looking at the total number of globular clusters within this galaxy and at the dynamics of these globular clusters. So because there is a relationship between the total number of globular clusters and the halo mass, they could put strong upper limit on the total mass of this galaxy. And as you can see here, the result was that this ultra-diffuse galaxy has a mass of about 8 times in 10 to the 10 solar masses, which is a typical mass of a dwarf galaxy, and is much smaller than what we expect for Milky Way. So by 2016, let's say, we knew that UDGs were found not only in clusters, they were found also in isolation. There was some first evidence that the mass of this galaxy was dwarf. And the question was then, how do they actually form? One initial hypothesis is that this galaxy could be formed just by assuming that they were the high spin tail of a normal population of dwarf galaxy. So if you had just normal galaxies, some of them statistically must reside into dark matter halos with a very high spin. The problem with this hypothesis is that since then, we have found some evidence that many UDGs do not show any rotation in their stellar component, and this is in contrast with this hypothesis. And so we try to study ourselves the emergence of ultra-diffuse galaxies. And the question that we want to answer is, can we understand the emergence of UDGs in a universe dominated by cold dark matter? To answer this question, we went and looked at simulations, and in particular, we used the hydrodynamical simulation from the NIHAO project, Hydrodynamical means that on top of dark matter, we also include gas, stars, and all the physics relevant to form a galaxy. This simulation reproduces 100 galaxies of different masses from Milky Way up here all the way down here to the scale of dwarf galaxies. And this is the stellar mass-Elo mass relation, or also called abundance matching relation that Julio just talked about in his talk. And so this is essentially a relation between the stellar mass of a galaxy and its dark matter content. And so all these balls, all these points are results from our simulation. So you can see how our simulation follow nicely the expectation of this relation. So one nice feature that I would like to mention, I can't talk too much about the simulation, but one nice feature that I would like to mention is the fact that we include supernova feedback in the simulation. This is the formation of a dwarf galaxy in the video that you are seeing. And this is a gas temperature map where red color represents hot gas. And you could see, especially at the beginning of the simulation, all these blobs of hot gas that just explodes and are driven outside of the center of the galaxy. So this is the effect of stars exploding as supernovae for stars larger than 8 solar masses. And essentially supernova feedback, as you know, is very important, not only because it regulates star formation in galaxies, but it's important in this case because it has an impact, it has a dynamical impact on the final distribution of matter within these galaxies. So it turns out, as you know, the prediction from running dark matter only simulation would be that every dark matter halo has a self-similar profile, which is called a Navarro-Franken-White profile. But the problem that also has been shown in previous talks is that some of the dwarf galaxy show a central, less steep profile, and this is what we call a core. So it turns out that you can form dark matter cores using this supernova feedback. And this is a very nice cartoon from a Nature review paper by Andrew Ponce and Fabio Governato in 2014 that explains essentially how supernova feedback can create cores. You can start with a dense star-forming cloud of gas at the center of the galaxy, which is this purple point, and you have a lot of dark matter particles orbiting around it. And at some point you have a bang, which is your supernova explosion. And so this explosion can evacuate from the center of the galaxy large amount of gas. And so what happens is that you are changing essentially the gravitational force that holds together all these dark matter particles orbiting around your galaxy. So gravitational force is insufficient and the particles migrate outwards on outer orbits. And this is how you can create dark matter cores in simulation. And it has been shown that this process is cumulative. So every time that a star formation region, you have a supernova explosion, you can exacerbate this process. Why am I telling you all this about core formation? Because it turns out that in our simulation and also in other group simulation, this core formation process is actually mass dependent. And it happens that the mass, the particular mass at which this core formation is mostly efficient corresponds exactly with the mass at which we observe ultra-diffuse galaxies. So this is an important plot to understand. On the vertical axis is the central dark matter slope of your galaxy. If you have an NFW profile, you have something between -1 and -1.5. If you have a central core, you have 0. And this is represented as a function of stellar over Elo mass. These different points, these different stars are points coming from a simulated galaxy. Each point is one simulated galaxy for which we calculated the central dark matter profiles. And so here you are seeing Nihao simulation and fire simulation. And the beauty of this plot is that it's showing you that simulation done with completely different codes and completely different feedback implementation give you the same result. And the result is that there is a specific point at which we expect core formation to be most efficient, which is this peak over here. And this point happened to be in the regime of bright dwarf or ultra-diffuse galaxy. So you can understand this plot as the dark matter profile essentially being determined by two opposite effects. From one side, you have the energy from supernova feedback, and from the other side, you have the gravitational potential energy on the underlying dark matter halo. So if you go up very low masses, you just don't have enough stars for the supernova feedback to have a strong effect. And if you go up very large Milky Way-like masses, then the gravitational potential of your 10 to the 12 halo is too big to be, let's say, contrasted just by supernova feedback. Instead, in this in-between regime, it's exactly where we can modify the central distribution of matter. So we went and searched for ultra-diffuse galaxies in our simulation, and surprisingly, we found many. This is an image of effective radius as a function of magnitude. All these black points are ultra-diffuse galaxies found in our simulation, overlap with observations. And one thing that I would like to stress out, we did not include, or we did not input any parameter ad hoc in our simulation in order to reproduce UDGs. So the fact that we just found UDGs in our already run simulation means that they are a prediction of our model. The nice things of having simulation is that instead of observation, we can actually observe directly what is the dark matter content of these galaxies, and we found that all the UDGs found in our simulation had a total dark matter halo of a dwarf galaxy. How do they form these UDGs in our simulation? Well, essentially the same mechanism that I just described that can form a central dark matter core also affects the stellar component of the galaxy. You can see here in the right plot, I'm showing the stellar density as a function of radius, and as you move from redshift 4 in green to redshift 0 in blue, you move from a very peaked and steep central distribution of star to a much flatter distribution. So the supernova feedback launching powerful gas outflows can have a dynamical effect not only on the dark matter but also on the stars. So that really your stellar distribution moves to outer part of the galaxy. And this is how you make a galaxy ultra diffuse. And this is an image in our simulation of a UDG.
Arianna, you have 2 minutes plus 5, okay? Sorry to interrupt you. Apologies.
So I think I will use some of the minutes of the questions. We put forward some observational prediction, and in particular, we put forward a prediction that ultra-diffuse galaxies could be found in isolation and they should be gas-rich. In fact, we predicted that some of the alpha-alpha survey, which is a H1 blind survey, some of the dark galaxies in the survey could have then been identified as being ultra-diffuse galaxies. And well, this is just to show you that for a same halo mass and stellar mass, galaxy with 2 orders of magnitude more H1 gas are also the ones that are more diffuse with a larger effective radius. So later on in the same year, the team from Alpha Alpha, in fact, found 115 isolated ultra-diffuse galaxies. They show that they were H1 gas-rich objects. This is a plot of H1 mass as a function of stellar mass. And these were the newly identified UDGs. And they also show for the 3 galaxies for which we have a mass decomposition as a function of radius, that their expected profile matches beautifully the profile coming from our simulations. So it's a sign that possibly these galaxies have a central core. So these are a few of the predictions that we put forward in this model. In red are the predictions have been verified observationally, and in blue the ones that are still work in progress that we would like to verify. Now, in the last few minutes of my talk, I like to move on some very famous example of ultra-diffuse galaxy. They made it all over the press, all over the world. One is Dragonfly 44, also known as the galaxy with too much dark matter. So Dragonfly 44 has been studied by Van Dokkum collaborator and has been claimed to have so many globular clusters, about 74, that essentially this would imply that its total dark matter halo was huge, much larger than what expected from its stellar mass. But there is a very recent paper from a group of people here at the ESC, a paper just appeared 2 months ago on arXiv, in which they re-derived the number of globular clusters for this galaxy. It turns out that the number is much less, about 18. And so with this small number, we can fit this galaxy within a normal dwarf galaxy dark matter halo of about 10 to the 11. And in fact, 10 to the 11 is also the favored dark matter halo that comes out just from simulation mass profiles in this plot over here, and also by fitting dark matter model to the velocity dispersion profile of Dragonfly 44. So this galaxy, after all, does not have too much dark matter. It seems to be just a normal dwarf. There was perhaps an even more famous galaxy called Dragonfly 2, which this paper was from the same author, Van Dokkum collaborator, a paper on Nature. They claimed that they found a galaxy with no dark matter. So the claim of detecting a galaxy at 20 megaparsec from us with little or no dark matter. Then a large collaborative effort from researchers at the Instituto de Astrofisica, led by Nacho Trujillo and included also myself. Essentially, people have re-derived the distance of this galaxy, and by placing this galaxy at 30 megaparsec, it means that now the stellar content of the galaxy is less, so it means that there is plenty of room for dark matter. And you can see in this plot, we are fitting with different profile, either an NFW or a chord worker profile. And in any case, this galaxy always seems to be more massive than 10 to the 9. So even this galaxy does not seem to be particularly strange. There is plenty of dark matter in this galaxy, although admittedly, this galaxy falls off of the M-star MLO relation. This is a plot showing the stellar content as a halo mass. These lines are the expectation from a Bindas matching, and these 3 points are the derived stellar mass halo mass for NGC Dragonfly 2. And so there is dark matter, but as you can see, is a bit scattered on the left side. And this is my very last slide, work that has just been submitted, well, that just been accepted and came out on arXiv like a few days ago. There was another galaxy that also been claimed to have no dark matter. And this paper by Mireia Montes and collaborator found that essentially they obtained optical imaging of Dragonfly 4, and they were able to detect tidal tails in this galaxy. And these tidal tails are caused by the interaction with this neighboring galaxy. So you can see in the left, the original image, in the right, the image obtained once removing the stars and the main galaxy. And so what does it mean? That the little amount of dark matter measured in this galaxy could be explained by the fact that this galaxy is being tidally stripped. So the conclusion of my talks are that ultra-diffuse galaxies are a natural outcome of lambda CDM models that includes the role of baryonic physics. Dark matter, but also star, can be modified in their distribution. We can form a central core, and this core formation happens to be most efficient exactly in the range of ultra-diffuse galaxies. We observe UDGs in clusters and isolations. Their halo mass always seems to be the mass of a dwarf galaxy. And at the moment, there is no evidence whatsoever for ultra-diffuse galaxy to be strange. So there is no evidence for any dark matter deficient galaxy, nor for any dark matter over-rich galaxy. Future avenues, of course, there is a lot to be understood. One possibility is that there are other formation channels for UDGs, especially in clusters. Another question is, why do some UDGs fall off of the baryonic-Tally-Fisher relation? There are some observed galaxies that seem to have way too many baryons compared to expectation. And so the future is rich in this sense. Thank you for your attention.
Thank you very much, Arianna. It was extremely interesting, and there's 3 questions for you, but unfortunately we have no time. So I do suggest to do the following with you and the other speakers, if you agree. Since we have quite a large break at the end of this session, that means after Kyle Oman's talk, people who are interested in asking a question, they maybe can stay here if you speakers are all going to stay. That sort of generate a pseudo discussion or a question session. If that's okay with you and you can stay, I think we can take the questions at the end.
Sure, I can stay, yeah.
Good. So I will thank you once again for the great talk, and we can pass on to the next speaker, who is Ryan Kipper, or Rain Kipper. Do I pronounce it incorrectly? I'm sure I'm pronouncing it incorrectly. But maybe Kipper, Rain? Okay, good. Great, I can see you. I'm gonna switch off my microphone and maybe you can switch on you.
Okay, hello from my side. My name is Ryan Kipper. So my topic is about lopsided galaxies.
Maybe you want to switch on the camera, and it's up to you, entirely up to you. And I will send you a chat and or interrupt you in 10 minutes from now, and then go ahead.
Okay, so my topic is the lopsided galaxies. And first, something about motivation. The dark matter searches, at least from my perspective, looks like this, that this is like saying that if it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. So the point seems to be that we must come to the same conclusion by very many ways. So in order to be sure what the dark matter really is. So most of the studying of dark matter so far is been about studying the distribution, how the dark matter is located inside the galaxy. But the thing that I will present is something about how the dark matter particles move around the galaxies, and yeah, this is the main motivation, how to study the dark matter as from many different perspectives as possible. So the main thing about the finding out how the dark matter moves is the dynamical friction. Actually, as far as I know, this is the only way how to study the movement of dark matter particles from observational point of view. And the dynamical friction works like if there is a massive object moving through particles, dark matter particles, it pulls the matter toward itself and kind of makes overdensity behind it. The overdensity is called the wake of the dark matter halo. The above is the equation how the dynamical friction works. And this equation contains the part called the velocity distribution. And if we are able to measure how effective the dynamical friction is, then we can estimate how the dark matter particles move inside the large-scale structure. And to put it more in a visual way, I calculated or just illustrated two specific cases. One case, the dark matter particles have practically no velocity dispersion. This corresponds to the extremely cold dark matter. And the other one for the case where there is significant velocity distribution of dark matter particles. As you can see, the wake behind the galaxy has overdensity. In one case, this overdensity is very concentrated and small behind the galaxy. And in the other case, this overdensity is like very smoothed out, and it's not very concrete, but it still exists. So if we can measure this density or the contrast of the wake, then we can say something about the velocity distribution of dark matter particles. So in order to connect theoretical aspects and observations, we need to select some galaxies that we wish to study. On the left side, there is a subset of galaxies that are called lopsided galaxies. These are galaxies that in the central part look like just every other galaxy, but the outer edges of the galaxies are highly distorted. And these are described as the center of the outer edges, and the inner parts are not concentric, meaning that the outer parts are distorted. And the other set of galaxies that show different behavior is the warped galaxies. The warped galaxies are just these galaxies that edges are like turned slightly up and slightly down for different sides. Usually, when people try to explain why these galaxies have this kind of morphology, there are few explanations. One explanation is that the gas is being accreted from one side that doesn't really fit, because if that's the case, then the kinematics should be based on infalling velocities, not rotation velocities. But the lopsidedness show the rotation velocities. The other reason is that the galaxies have interacted. They have either merged with other galaxies or they have just had quick flybys by other galaxies, and they have kind of distorted tidally the main galaxy, and this causes the asymmetry of the galaxy. This doesn't always fit because there are lopsided galaxies that are in quite isolation. They have no companions nearby, so there must be some other way in addition to the flybys. And in this paper, we studied the possibility that the wake of the dynamical friction causes the tidal forces inside the galaxy, and this will show up as a lopsidedness. Basically, behind this galaxy, on the left image, there should be some kind of dark matter wake, which pulls one side of the galaxy more strongly than the other side, and this could cause the lopsided behavior of the galaxy. So this is the thing which was that I was trying to estimate or study. And in order to find conditions that I can be sure that this is really caused by the dynamical friction, tidal field of the wake from the dynamical friction, there must be main condition that is that this galaxy must be as isolated as possible from the other galaxies. So the other reasons cannot be the root cause of the lopsidedness. And this means that this galaxy must be inside the void or some other region where the environment doesn't affect so much. And the plus side, from the theoretical point of view, is that if we find some kind of region where there is nothing nearby, then the velocity distribution of the dark matter particles that we infer will be the mean cosmological ones, or at least as close as possible to that. Not the kinematics or dynamics of the halo itself, of the cluster environment. So this provides the possibility to study the average, universal averages of the velocity or temperature of the dark matter particles. Seems that the system is frozen.
Ryan, is it all good? We can see you all right. Actually, that's your timer that is saying you have 5 minutes. We can see you.
Can you see my slides also? Because I cannot switch anything to slides or.
We are seeing a slide that is called the environment, and it was there for a little bit while. There is an image from the Millennium mission on the right, and there is a galaxy with a green circle and a tidal thingy in red.
Yeah, I can see only the same picture myself, but I cannot change the slide for some reason.
You stop sharing. Maybe you can stop sharing.
I don't have any cursor also.
You stop sharing and then try and share again. That solves it.
I cannot stop sharing also because my screen is frozen. Can you make me stop sharing?
I will stop your camera first. Okay, stop video.
Okay.
Okay. Now I will do something like, I don't know if I can disconnect you. Okay. All right, I managed.
Yeah, now it works again.
Okay. Now you can try and share it again. Okay.
Okay. Can you see it now again?
Maybe don't use the camera because it probably overloads the computer.
Okay, I will. Can you see this next slide at the moment?
We are on our test galaxy right now, which seems to be the slide.
Yeah, okay.
Okay, good.
So I will continue from here.
Troubleshooting.
Okay, I will hurry up. So this is our test galaxy that we wish to model the dark matter dynamical friction. And we selected this galaxy to be as isolated as possible first. And the second condition was that it should have the best available observations as possible. So it has been observed with H1 velocities and the H1 distribution data group from radio observations. So we started modeling, and we found out that this kind of wake of the dynamical friction can produce strong enough tidal forces to have the galaxy turn into a lopsided one. And here is shown the geometry of the system, that if the galaxy moves H1 toward from the dynamical dark matter particles, it causes the lopsidedness. And if it moves like face on, then it causes the U-shaped warped galaxies. And the intermediate angles, it causes both warped galaxies and lopsided galaxies. So we tested the dark matter density, how much should be the dark matter density in order to be observed as lopsided galaxies. We can see that comparing the black line that shows the galaxy itself and the bluish points that corresponds to the wake, acceleration caused by the wake of the dark matter density, then we can see that depending on radius, there is at least some observational effects almost guaranteed to be observed in almost any environment. And the third one, we studied the temperature dependence or the velocity dispersion of the dark matter particles. And we can see that, yes, the dependence is strong enough to distinguish different dark matter velocity distributions. So quickly passing this one and telling that we made quite good match with the observations by making this modeling. So we were able to infer the dark matter velocity distribution quite well. And the overall result is on the plot on the right, that the dark matter velocity distribution inside the voids that are not bound to the galaxy is about 20 kilometers per second. Due to some specifics of the modeling, we cannot say that whether it's, we can say only the order of magnitude. It's not like a concrete value. We can be sure that it's below 80, but we cannot actually distinguish between 20 and 0 because of the details of the modeling. And we were able to infer the density of the dark matter that was causing the tidal fields. And I think I will leave with conclusions here because I think my time is up.
Yeah, your time is up, but you have approximately 5 minutes for questions. And so if you want to use 1 or 2 of your minutes to stress some particular point.
Yeah, I think that the best point is that this allows to infer the dynamics that is inside the void regions or just in empty regions. And this is, I think at least, should be best available to be best comparable with the theoretical models, because they are not affected by the internal dynamics of the cluster or other kind of environments. And I think that's all from my side.
Thank you very much, Ryan. Are there any questions, Ryan?
Okay, I have a question.
Who is there? Can you say your name?
José Sanchez Almeda. I'm the next speaker.
Please,
so the question is about whether if this effect is at work, it should affect all galaxies. So I would expect, I mean, all galaxies have dark matter around. So I would expect that all galaxies are showing some effects of lopsidedness or any of the things that you expect from the dynamical friction that you are describing. Is this correct?
Yes, actually, it's most, or at least within, let's say, 15 kiloparsecs, that about third of the galaxies show lopsidedness. And as far as you go outer parts of the galaxies, the lopsidedness increases. So in principle, there should be all galaxies should have some degree of lopsidedness. So it's, in a way, it's correct, yes. And this, from the modeling perspective, it depends on how fast the galaxy is moving with respect to the dark matter. If it stays still, like it moves with the flow, then there is no lopsidedness expected. At least from the dynamical friction. There can be from mergers and other processes.
Jorge, are you satisfied with the answer?
Yeah, fine. That's perfect. So thank you.
Mm-hmm. All right. So is there any other question for Ryan? Well, if no, we should thank him then and move on to Jorge. And thank you very much, Ryan, for staying perfectly within the time. I am not occupying it entirely so that we can perhaps finish a few minutes earlier and prolong the session of questions at the very end of this session. Jorge, you are up. We are seeing your presentation now, and I will give you the 10 minutes notice when you're past 10 minutes, so you will have then 5 plus 5. Again, if someone has questions for Jorge, maybe start sending them in the chat to me only, and then I will collect them. And also, yeah, nothing else. Please go ahead, Jorge.
Okay, well, first of all, thank you very much for allowing me to present our work on why the principle of maximum entropy explains the course observed in dwarf galaxies. This is a work carried out in collaboration with Ignacio Trujillo and Ángel Plastino, and it appeared like a month ago or so in ANA. And this is the full reference, if you can see the point. I think you can. Now, my presentation will follow this. Let me check whether, do I have the camera on? Yes, I do.
You have the camera on and you are seeing, okay, now we're seeing outline.
Okay, so this is the outline of the talk. First, I will talk about the motivation, the reason why we carried out this work. Then I have to talk about self-gravitating systems of maximum entropy. I will point out that those systems, the density that you expect from self-gravitating systems of maximum entropy are polytropes. And then I will explain that dwarf galaxies show cores which are very consistent with polytropes. And finally, I will spend a couple of minutes talking about potential implications of this result. So it's obvious that in this forum, I don't have to work very hard to explain the interest of understanding the nature and the behavior of dark matter. Let me recall something that may be obvious for those that are doing astrophysics, but may be not so obvious for the rest of the people, is that dark matter, among many of the things, provide most of the gravitational force that allow galaxies to be formed in a time scale which is compatible with the age of the universe. Okay, focusing on the topic of the presentation, most astronomical objects, this is an observational result, show cores. Cores in this context means that if you manage to determine a density and how it varies with the position from the center of the structure, this is a globular cluster, so this is the density. The density has a plateau in the center, so this is called core. And this appears, for instance, in a globular cluster. This is a purely stellar system, so it doesn't have dark matter in, and it shows a core, and it has typically 10 to the 6, 10 to the 5 solar masses or so. But if you move to massive elliptical, 10 to the 13, 10 to the 14 solar masses, so like almost 10 orders of magnitude more massive than the globular light cluster, you find cores as well. And if you go to the middle, so dwarf galaxies, again, the density profile and the way it varies with radius has a plateau in the center, so a core. Now, together with this thing, which is purely observational, we know that the numerical simulations of cold dark matter, as the one that has been discussed at the beginning of the session, they don't have cores. They produce density profiles that keep growing towards the center, Navarro Franklin White or in Astro profile. Okay. Now, I've been talking about observations and numerical simulations. What about theory? Now, suppose that you have a self-gravitating system and you wait for some time, long enough, for the system to reach some sort of thermodynamic equilibrium. So you expect that over time, your system evolves to a configuration that maximizes the entropy, or in the parlance that I'm going to use, is in thermodynamic equilibrium. You just have to wait long enough. Now, if you play the game of characterizing this thermodynamic equilibrium with the classical Boltzmann-Gibbs entropy, and you ask a system that maximizes this entropy to be self-gravitating, then you end up with isothermal spheres, which has the unpleasant property of having an infinite mass. Okay, now, like 25 years ago or so, Plastino and Plastino pointed out that if you replace the Boltzmann-Gibbs entropy by the Salis entropy, which is suitable for systems with long-range interaction, such as gravity, then what you get is a density profile that is called a polytrope. And these polytropes, among other things, have the nice property of showing cores in a natural way. Now, in order to put this in the right context, I had to emphasize that the Boltzmann-Gibbs entropy is just a limiting case of the Salis entropy. So the isothermal sphere, the solution of the Gibbs entropy, is just a limiting case of the polytropes that I'm going to describe next. So what are polytropes? Polytropes are solutions of so-called Leinen equation, which is this differential equation here, for something like the gravitational potential. This is phi here, and depend on an index m, which is called the polytropic index. Actually, the density that is predicted for this polytrope, for these thermodynamic equilibrium solutions, depends on the polytropic index, and then in two other three parameters. One that scales the x-axis, the y-axis, and the other one scales the x-axis. And m gives the shape of the polytrope. So you change m and you change the shape of the polytrope. Now, one of the good properties of these polytropes is the fact that they have a finite mass. Remember that the isothermal sphere has an infinite mass, at least for an index smaller than phi. Another property that is important in this context is the fact that they have cores. So the density profile, the way it varies with radius, has a plateau in the core. And even more, this core is the same for all polytropes. It does not depend on the polytropic index in the following sense. So if you rescale all the polytropes, because I mean, somehow you remove the dependence on the scaling in x and y, for instance, normalizing by the density and the radius when the logarithmic derivative of density reaches a given value, then all polytropes are basically the same. This plot here, density versus radius, shows three different polytropes going from index infinity, which is associated with the isothermal sphere, to a small value. So very different at large radii, but all are the same in their cores. Now, the obvious question is whether these cores that are predicted by the polytropes are consistent with the cores that we observe in astronomical objects. And we are in a kind of project trying to see whether we can say something about this thing. The first step was to try to see whether we can reproduce the cores observed in dwarf galaxies. You can determine the density profile of dwarf galaxies with all the uncertainties of all the observational uncertainties that have been mentioned in the previous talks, from the H1 rotation curves. And remember that dwarf galaxies are galaxies that are dominated, the potential is dominated by dark matter. Therefore, basically, the density that you obtain is the density of the dark matter. Now, observationally, it has been shown that the density profiles of a collection of galaxies, they all collapse to a single shape if you normalize to a density and a radius given by the logarithm derivative to be fixed, or something like that, similar to what I tried to explain in the previous viewer. And this is what is shown here as a blue dots and a shaded blue region. This is the shape of the density profile collapse to show a given single shape. Now, in this representation, polytropes have only, sorry, in this representation, polytropes don't have any degree of freedom. They are just fixed. And polytropes, as you can see, which are the colored lines here, they match extremely well the observed chord in dwarf galaxies. Now, the conclusion is that the cores observed in dwarf galaxies are consistent with the structures expected from thermodynamic equilibrium. So you can say that the cores in dwarf galaxies seems to be in thermodynamic equilibrium. Now, what could be the implications of these results? First, as again we have heard in the previous talks, it's not trivial to have a pure dark matter profile made of dark matter particles which are collisionless in equilibrium. So one had to manage to find a way in which the system of dark matter particles can reach thermodynamic equilibrium. One of the possibilities is what Arianna was discussing, is the feedback of baryons on the dark matter potential. So through gravity, baryon-driven events can modify the overall gravitational potential and produce a core, somehow thermalizing the system. Another possibility is that the dark matter is not really collisionless, but it has collisions, it's self-interacting. And then, depending on the collision cross-section, you can reduce the time scale to reach equilibrium and in a finite time, so in a time scale smaller than the age of the universe, to have a dark matter profile that is in equilibrium, at least in the center. Maybe dark matter, sorry, maybe warm dark matter might do something similar. I don't really know. And another possibility is that the dark matter is made not of elemental particles, but of massive objects like intermediate black holes. Because in this case, the time scale for thermalization, which depends basically on the number of particles that you have, is much, much smaller than the one that you might have if you have tiny little particles, millions of tiny little particles describing the potential. So
we have 3 minutes plus 5. Sorry.
Okay, so I'm almost done. So I just wanted to say that suppose that I have been just describing what happened with dwarf galaxies, but suppose for a moment that not just the dark matter halos associated with the dwarf galaxies, but all dark matter halos are in thermodynamic equilibrium. So all of them show cores. So these have implications on the estimate of the gamma ray fluxes to be expected by self-annihilation. So you're basically dropping the density by a factor of 10. And this has an impact on what the fluxes are to be expected. Suppose that we are using gravitational lenses as a tool in astrophysics. And again, it's important to have a good model of the lens if you want to use the lenses for things like studying the evolution of the Hubble constant with time, which is popular nowadays. And finally, let me address something else, which is why the cold dark matter numerical simulations that we have hearing about produce Cusp. And at the same time, I'm saying that from thermodynamic equilibrium, you expect cores in a system of gravitationally bound particles, basically. So I'm messing up several things here, but the only thing that I want to say is the following. It's cold dark matter numerical simulations produce cusps rather than cores, and from theory, we expect cores. How these two things can be reconciled? And they can, because the numerical simulations of cold dark matter are not allowed to reach thermodynamic equilibrium. If you allow for a simulation to reach thermodynamic equilibrium, and this is what is happening when you are modeling self-interacting dark matter, then you produce cores, this we all know, cores which are polytropes in shape. So thank you very much. And this is all what I wanted to say. I'm ready to take questions if you like.
Thank you very much for staying in the time. Is there, and I know that there is one question for Jorge, unless I think you have a little bit, at least 1 minute more, unless you want to say something else. I'll just address the questions, right? So there is, I'll read a question that's coming from Carlos Arguelles, who's in Argentina, and he's saying, has it been shown already that other entropy functionals, such as Lindenthal entropy or Fermi-Dirac entropy, can lead to core profiles within maximum entropy in principle? That's, I think this is a statement. It is, how this initial result compares with the former? Could you comment on that, please?
No, I think that, yes, it's true that the Salles entropy is not the only way in which you can get cores. But the point here is that the cores that are predicted by the Salles entropy are the cores that are observed in dwarf galaxies. That's the issue. Okay, whether it is the only way in which you can reproduce these cores, we don't know. We don't claim anything about this thing. So, in principle, I say basically that either you take the Salles entropy, even the Boltzmann-Gibbs entropy, which is a limiting case for the Salles entropy, it also produces cores. So probably there are more than one way in which you can get the cores. But the cores somehow are telling us that the system is in thermodynamic equilibrium.
Okay. Carlos, I hope that answers your question. And if there is is there any other question for Jorge specifically? 1, 2. If not, then I will take, there is a generic question that I think is from a student, I suspect, but I'm not 100% sure. And so the question is, and I guess it's for all the speakers, what physical mechanism the feedback from baryons can, well, I guess, well, the writing says, what physical mechanism the feedback from baryons can influence the dark matter to acquire thermodynamical equilibrium? I guess the question is, what is the mechanism that can make the baryons acquire thermodynamical equilibrium and the dark matter within the halo? So I guess that probably the question is about the realization shock or something of the kind. Rafael, if you are there, you have 1 or 2 minutes for your question. If any of the speakers would like to take this question, which I think is
I think I tried to answer this question. So it might be something that was pointed out by Governato et al. And Arianna Di Cintio explained. Basically, one of the possibilities is to move in and out matter that you have in the center of the gravitational potential. And through the changes in the gravitational potential, you can change the distribution of dark matter. And you can do that in time scale which is shorter than time scale that a pure dark matter profile would have for evolution. And so this allows the system to reach thermodynamic equilibrium. Another possibility is having self-interacting dark matter. And so again, you have collisions between dark matter particles. And this drops the time scale to set the gravitational collision. Another possibility is that the dark matter is formed by massive objects like black holes. because
I guess we're going to stay on the most generic, right? Let's just take the first answer, which is valid for everybody, right? And I think Julio also wants to comment on that. Julio, you want to take the microphone?
Yes, thanks, Xavier. There's a bit of, not confusion here, but a lot of jargon that we need to clarify. I mean, a self-gravitating system of collisionless particles does not have a state of maximum entropy. Right? So you can always increase the entropy of that system by pushing particles to infinity and by making the system a bit more centrally concentrated. In other words, you'll take a system of collisionless particles and somehow make a black hole in the center and put the rest of the particles in infinity. That has much more entropy than any other one. So all these issues come to definitions of entropy that are necessarily limited and that somehow force the solution to be whatever it is that you want to get. So you can define entropies in different ways, and then you get different profiles, so different equilibrium things. But I'm not sure that there is anything beyond that. I mean, how useful that is or not is not completely clear to me. In the case of the collisional system, the problem is that there is no mechanism to make things to be in thermodynamic equilibrium. Equilibrium requires basically collisions. So without collisions, without a way of thermalizing the system, it cannot work. So if you adopted the black matter is collisionless, then searching for the thermodynamic equilibrium option is not valid. I mean, this is not the physics that the problem that we're talking about, and that's why the numerical simulations, the Cusp profiles, are really telling you more about the initial conditions that lead to that formation rather than a relaxation process of what happens after the system is put together. So I was mentioning before that we understand the NFW profile more as a result of how the matter is put together as a function of time rather than as a result of what happens after the system is put in place. And I think that is the correct description of what happens, at least in the case of collisionless cold dark matter. Of course, if we change that and make other assumptions, of course, the results may change. But I don't think this assuming maximum entropy is a particularly useful approximation in the case of vanilla cold dark matter, at least.
Can I comment on that?
We have 1 minute, and then we can go on the. I'll give
well, it's simply saying that. I mean, of course, I'm not gonna. You are the expert in the field, so perfectly. But if I understand what cold dark matter means, is that, of course, you have collisions, but the collisions are through gravitational interaction, and they are extremely inefficient. So you have to wait for very, very long, or have very massive particles. So if you have elementary particles describing the dark matter, then you have to wait forever. So you will never reach equilibrium. But you can reach equilibrium even in a collisionless system of massive particles, like black holes of 10 to the 6, 10 to the 4, 10 to the 6 solar masses in a reasonable time scale. So collisionless means that the collisions are through gravitational interaction. And this is very, very inefficient if the particles are very low mass, and not so inefficient if they have a significant mass.
Well, collisions means that collisions are unimportant, relative to in an orbit. So in other words, in an orbit of a particle around the system, you're moving in the mean potential, and you're not influenced by collisions with other elements of the system. So the collisions could be gravitational, or anything else. So if you see something that is evolving on the time scale, it means that it's not collisionless. We call it collisional, like in a globular cluster, for example. An example, systems of point stars where collisions are important, and we know that they are important. But that is not the case for cold dark matter, at least in the way we usually understand cold dark matter.
Thank you very much, Julio. I think we can, if there is further discussion about this, which I find fascinating, we should defer it to the question session, to the break session, which is right after Kyle's talk. So please don't go away. Kyle, if you can start setting up your screen. And right after Kyle's talk, we will then go for one generic picture. So at that time, I will ask you to switch on your camera, and then we I have a list of questions also for the previous speakers. So if at least the speakers and those who ask questions want to stay on during the break. Okay, Kyle, please go ahead. I will let you know in 10 minutes from now that you are half the way. Okay.
Okay, thanks. So thanks very much to the organizers for giving me the opportunity to talk. I just want to tell you about an explanation for the diversity of dwarf galaxy rotation curves, which is going to, in a lot of ways, pick up on themes in Julio's talk and in several of the other talks of the session. All right, so this is about constraining the properties of dark matter, in particular how dark matter is distributed within galaxies from the gas kinematics observed for those galaxies. Okay, and to just boil this down to the very most simplistic picture I can paint here, right? So in the ideal case, the gas kinematics in a galaxy through their rotation curve trace the circular velocity of the system, and then you get a very simple relationship between the rotation speed on an orbit and the mass enclosed within that orbit, right? And built into this are a number of assumptions. So this assumes that the system's in equilibrium. It assumes that the tracer particles are on circular orbits. It assumes that the system is spherically symmetric. And I'll be talking about gas disks, but for the systems I'll be talking about, the potential is actually dominated by the dark matter. So the potential is, well, it's not disk-like. It's much closer to spherical than it is to a disk. And also assumes that the system's under pure rotation under gravity. So for instance, that other sources of support for the system, such as hydrostatic pressure, are negligible. And in reality, when we observe galaxies and try and measure the rotation curves and model them, all of these assumptions can be relaxed somewhat, and some of them will introduce errors, while others we know how to handle. And so I'll touch on that as we go along. Okay, and so I'll just quickly flash this up here because it's been discussed now many times in this session. But just to remind you that, so the rotation curve, where again, kind of thinking of the circular velocity and the enclosed mass, gives me a relationship between the density profile of dark matter illustrated on the left here. So I've got the classical NFW profile in blue here, which rises steeply towards small radii. And then on the right, the corresponding rotation curve, just assuming this equation at the top, which has this characteristic sort of steep rise near the center, and eventually reaches some maximum velocity, which is tightly correlated with the total mass of the system. And then just to illustrate here, I've got a cartoon dark matter core. So I follow the NFW profile, and then I've just cut it off at some constant density. And on the right, the rotation curve corresponding to that galaxy, density profile, has this characteristic linear rise near the center. Right? And just to guide the eye, I've labeled the same radius in both panels with this arrow. So you see up to the radius where the density begins to drop, you get this linear rise. Okay, so we've talked a lot about the sort of conflict, potential conflict between the dark matter cusps predicted by n-body simulations and the apparent observed cores in many galaxies. And so I just want to kind of give a quick bird's eye view of the solution space to this tension, right? So to reconcile these, I think this covers all the possibilities. So you can either argue that the dark matter is not cuspy because it's been redistributed in the process of galaxy formation. So I'm thinking of things like violent motions of gas gravitationally coupled to the dark matter, redistributing it. Or it could be that the dark matter is redistributed by the dark matter physics itself. So if I had a scattering interaction between dark matter particles, for instance, that might limit the central density. Or it could be that this is, that we're not correctly inferring the mass distribution because we've assumed the wrong law of gravity. So if you assume a non-GR gravity law, then that could reconcile these two things. Or you could try to appeal to errors in the modeling and interpretation of the data. And that'll be, this last point will be sort of the focus of the rest of the talk, looking at how far we can get with that. So Julio showed the right half of this plot in his talk, pointing out that the rotation curves of pure CDM halos, so for instance, in a simulation where there's no physics other than gravity and no species other than dark matter in the universe, So you get these nice self-similar rotation curves, which if you translate them in this space, will all lie on top of each other. And so this sort of self-similar property of the rotation curves, or equivalently in this context, the density profiles, ends up being broken by galaxy formation. So I illustrate this on the left. So the black curves are just repeated. And then these are for, so now a simulation which includes galaxy formation. You can see that for low mass galaxies, or equivalently low maximum circular velocity, the rotation curves are not particularly different than they were before. But as I go up to higher mass galaxies, the fact that I've assembled a galaxy that is actually quite massive in the center of the system, right, so in the central, say, 10 kiloparsecs or so, drives up the central rotation speed, just because I've added a lot of extra mass relative to what would be there if there was only dark matter. Okay, and this will come back in a few slides. So yeah, in contrast to the sort of generic self-similar rotation curve prediction from pure CDM, right, the observed situation looks like this, and Julio also showed this slide, so I won't dwell on it too long, but this is just a selection of 4 dwarf galaxies chosen to have about the same maximum circular velocity, or same total dynamical mass. And you can see that they go from very steeply rising in the center all the way to this very gradual rise. And I told you a linear rise corresponds to a flat density profile. And so this is sort of the poster child for a dark matter core. So now to try and put many galaxies on one figure, this is what we came up with a few years back. So here I'm plotting Vmax on the x-axis. So this is the maximum of the rotation curve, which has been mentioned many times, correlates with the total dynamical mass of the system. And then on the other axis, I'm putting the measured rotation curve at some fixed radius, so 2 kiloparsecs. And the idea is that this should be some small radius, so it's in the central regions of the galaxy. And 2 kiloparsecs was as small as we were comfortable making this at the time, given the resolution of the simulations we wanted to put on this plot and the observations that we wanted to put on this plot. So there's no particular reason for this magic number other than it's resolved enough for our purposes here, right? And so if you take the NFW profile, because NFW profiles are self-similar, you get a very straightforward correlation between the rotation speed at maximum and the rotation speed at some fixed radius. And that's indicated by the solid line. And then just to illustrate here, if I chop out some fixed amount of mass, I chop out 10 to the 8 solar masses from the central 2 kiloparsecs, then that will bring the correlation down here. And as I chop out more and more mass from the center, I get further and further down. So basically, cuspy profiles lie along this solid line, whereas chord profiles lie below. So if I put a dark matter only simulation on here, unsurprisingly, the points lie directly along the NFW curve. So that's a nice sanity check. If I put on points taken from galaxies in a simulation with full galaxy formation physics, then I get something that looks like this. So it follows along nicely for low mass galaxies, and then the higher mass galaxies begin to bend up from the solid line here. And this is just going back to what I showed before, right? You're assembling a massive galaxy in the center of these systems. So you're adding a lot of extra mass in the center relative to what you would have with just the dark matter halo, which drives up the rotation velocity. Right, now I can put some data on here. So this is a compilation of many different surveys that we put together a few years ago. And you can see that, okay, they lie kind of all over here. You have everything from galaxies with a very steeply rising rotation curve to galaxies with very slowly rising rotation curves down near the bottom. And so now the question becomes, how do we explain this? The simulation I just showed you doesn't appear to do a very good job, so what's missing? And so I'll just try and illustrate that for the rest of the talk. So I'll tidy up the observations a little bit just to make some space, and I'll just keep 2 particularly well-known surveys on here, and put back a few simulated galaxies in red here. So these are simulated galaxies selected in a particular range of maximum circular velocity. So these are basically the bright dwarfs, as Arianna called them. And this range is particularly interesting because this is where people argue that you might be able to form cores through baryonic feedback. These particular simulations don't do that. And then there's also the advantage that these are still low enough mass that they're not completely dominated by the baryonic mass distribution near the center. Okay, and so the red points here are taken from the circular velocity profile. So that's the rotation curve I get if I take the mass distribution of the galaxy and just turn it into a rotation curve through that simple equation I showed back near the beginning. I can look
you're approximately halfway. Sorry to interrupt you.
Okay, thank you. I can look at the gas in these galaxies in the simulation, which is in a disk typically, and is rotating. And I can look at the rotation speed of that gas in the simulation. And so that's what I'm showing it with the green points here, is if I construct a rotation curve by actually measuring the azimuthal velocity of the gas in these systems, I get these green points. And so there's a pair for each of the red points. And the point here is that the green points lie close to the red points. And so these systems have a gas disk which is rotating at about the circular speed. And okay, great. Now what I want to do next is show you what happens if I take these galaxies and I try to observe them. So I take my simulation and I treat it like an observational data set. So here's an example for one of these simulated galaxies. I've gone and I've constructed a data set analogous to what you'd get from a radio telescope observation of the 21 centimeter line from neutral hydrogen. And so when you measure that, you get simultaneous imaging and spectroscopy across the whole field of view, at least if you use the right kind of telescope. And so here I'm showing a few projections of the data. So on the left, this is the surface density of the neutral gas. And in the middle is of particular interest, this is the velocity field. So it's the average velocity along each sight line, which we can measure because this is a spectral line. And so we get a spectrum in each pixel. Now I'll show you what happens because this is a simulation. I can do some neat things. So I can take this disk, which is inclined sort of 60 degrees towards you, and then I can spin it around the pole of the galaxy. So this is keeping the inclination fixed, but just many different sight lines to the same galaxy at that fixed inclination. And so you can see this is obviously not an axisymmetric system. Okay, and then if I take these mock observations and feed them through the sort of modeling pipeline that observers use on these kinds of observations, I can reconstruct the rotation curve for each of these mock observations. And so that's what I have here. So again, I've got the inset that I just showed. The red curve here is the circular velocity curve. The bluish curve is the actual rotation speed of the gas in the simulation. And then in black is what I get if I go and try and model this particular mock observation. Right, so here I'm getting somewhat an overestimate of the actual gas rotation speed and also of the circular velocity, particularly in the inner regions, say around 2 kiloparsecs, where this is of particular interest in this context. I can show you what happens as I spin this galaxy around, right? So this black line jumps around. I get very different estimates of the rotation curve as I spin this thing around. And so for 24 different sight lines spaced around the galaxy, you can see there's quite a large scatter. So the obvious question is, why does this happen? And so at least for these simulations, we've traced this back to non-circular orbits of the gas in these simulations. So the disks, or the gas going around the disks is not going around in perfect circles. It's a little bit elongated. That elongation turns out to be due to the elongation of the dark matter halo, which is not perfectly spherical. So the disk is pulled a little bit along the same axis where the halo is elongated. And then it becomes a matter of how the sight line to the galaxy lands relative to that elongated orbit. And so if the major axis, so the long axis of the galaxy when observed, has some gas at that particular position, which is moving a little bit faster than average, which is illustrated in blue over here, then I'll tend to overestimate the rotation curve a little bit, whereas if it's a little bit slower than average, then I'll tend to underestimate it. And that's just because that major axis of the galaxy is where you get most of the information, because that's where you have gas that's moving along the line of sight to the galaxy, as opposed to in the plane of the sky. And it's only that motion along the line of sight that we can measure by its Doppler shift. And so then if I take this sample of galaxies and I take one random sight line to each and then reconstruct its rotation curve and plot what I get back in this plot, I get these black points, which you see have scattered around quite a lot. And basically the large scatter here comes from what I just described, right? This is the elongation of the orbits, basically is randomly aligned with the sightline to the galaxy, and so then I either over or estimate these on an individual basis. You also notice that these are systematically shifted down from where they should be, which is the red points. And that we've traced back to the thickness of the gas disks. And so basically you're confusing many different heights in the disk and radii in the disk along a single sight line because the disk is geometrically thick. And so that causes some problems, which I won't go into the details of that for lack of time. And then Julio showed this plot showing that this eta rot parameter and eta bar parameter, which I'll remind you, basically have to do with how cored or cuspy the dark matter halo is and how centrally dark matter dominated or baryon dominated the kinematics are. For dwarf galaxies, which are the darker orange points here, are anti-correlated. And it turns out that the kind of errors you make just from these sorts of issues reproduce this quite nicely. So this is shown for two examples here. So the circular velocity curves of these simulated galaxies are shown by little crosses, and then we pick out two, this big red box and this big blue box. So this is the correct answer for these two galaxies. And then when we go and do this forward modeling process for many different sight lines, we get the small boxes of the corresponding colors, which scatter diagonally with this anti-correlated pattern. So that's intriguing, suggesting that maybe these kinds of errors are actually operating for real galaxies. I'll show you one other piece of evidence that suggests that this might actually apply in the real universe. So I just want to highlight these two galaxies, which have very high quality data, very high quality measurements, and which look like they have quite a large dark matter core. And before I show you the actual data, I'll just highlight that. So if I observe the velocity field of a galaxy and it looks like this, and then I subtract the mean rotation, I'll be left with some residual, and the signature of these non-circular motions, if it looks like what I have on the right here, where I have sort of this 3 red peaks and 3 blue peaks, and the red peak lands on the blue side of the galaxy, that's the signature that I should underestimate this rotation curve. If I have the same pattern but reflected, then I should overestimate the rotation curve, and then there's a situation where it's also unchanged. Okay, so here's the data for DDO 47 and DDO 87, these two dwarf galaxies as observed.
I'm very close to the end of your time.
Okay, I think I have one more slide, so thanks. The modeled rotation fields of these two galaxies are in the middle, and then the residuals are on the right. And okay, this is, I'm not going to call this conclusive evidence, but if you squint a little bit, you might convince yourself that there's a sort of 3 blue peaks and 3 red peaks here oriented in about the right way. And then similarly for this other one, 3 redder peaks and 3 bluer peaks, again, roughly oriented as would be required to cause an underestimate of the rotation curve. And then I think the one more piece of the story that I'll add here is that, so this is all well and good, but the galaxies I was showing you were selected such that they have gas that is behaving reasonably well and rotating at roughly the circular speed. Here's a slightly wider selection where that constraint is relaxed. And so you can see the example I showed before is up in the top left here, but there are other galaxies where the gas is not rotating at the circular speed. And these could be quite problematic because you can see, the recovered rotation curves in black typically trace the actual rotation speed of the gas if you could average over all sight lines. And the implication there being that if you built up a large enough sample of galaxies and kind of averaged over them, then you might get the right answer. But the problem is that if the gas rotation doesn't actually trace the circular velocity, then it's not actually telling you what you want to know about the mass distribution. And you're going to make an incorrect inference on the dark matter distribution in these objects. And that's still kind of an open problem. How do you identify which systems have kinematics that is actually tracing the underlying mass distribution like you think it is? So that just brings me to my summary. So there's a wide diversity in the shapes of galaxy rotation curves. And how bad the cusp core problem looks is probably not as bad as it looks at a glance once you account for these kinds of systematic errors in the modeling. And I think another takeaway is that this forward modeling process where you really treat numerical simulations as observations is really crucial to leveraging their full potential. And the key references are at the bottom there if you want to go read more. Thank you very much.
Thank you very much, Kyle. Is there any question for Kyle? Anybody? Okay, so before getting, oh, there was the timer, perfectly, you stayed perfectly on time. So before getting on to the session, like we can use these next 15 minutes, if the speakers agree, to continue the discussion and take a couple of questions that were asked previously. We have
future perspective to explain in a more natural way with baryonic physics, the small scatter of the baryonic Diffusion relation, the mass discrepancy acceleration relation, and the radial acceleration relation. And besides the small scatter, also the lack of correlations between the residuals and the galaxy properties.
Yeah, yes, thank you, Valentina, for the question. I mean, we've actually looked at all those questions already in several papers. I can pass you the references privately, by private email if you want. And we've, what we learned is that those are, the predictions from the simulations are actually well consistent with the observational scatter. To give you an example, the Thaler-Fisher relation, for example, in the simulations, if you look at the scatter and Thaler-Fisher relation that you get, is actually much smaller than the observed one, as it should be, because in an observations we have observational errors. In the simulations we presumably we don't, or they're smaller, at least in that, from that sense. The same for the mass discrepancy acceleration relation. That is actually a natural result in cold dark matter of the NFW profile and the way in which galaxies populate, the dark matter halos. So I can point you also to papers that we discussed that. So I haven't seen any. So I think all those things are actually not very naturally explained, and without any resorting to any, extra parameters or anything else. The problem I think that remains is really the very inner regions, the very inner cores of galaxies, where, as Kyle was just describing, there seems to be quite a large, variation or diversity in the properties of the inferred properties of dark matter from rotation curves. And well, as you see, what Kyle was proposing is that actually there isn't, and that a lot of that maybe just due to the fact that we're interpreting data in a way that doesn't allow properly for the uncertainties in the cyclical velocity estimates. But I mean, I can discuss, of course, much more in detail if you want, but I can also send you references to the work that I mentioned.
So yes, thank you. They would be useful.
Okay, thank you very much, Julio. Thank you very much, Valentina, for the question. There's a request for Umberto to show the video. Umberto, if you're still there and you still want to show the video, but I can see Umberto.
Yeah, I'm still here.
Yes, I can see you. You want to show that video, Alexei, that you wanted to show in reply to Alexei?
Yeah, just a second.
Get passed on to Arianna. And Arianna, maybe you want to pick one of the three to answer, if you have the answer. And maybe also read the question, because the other people don't know what the question is.
No, I mean, I can quickly answer to all of them because I don't have the answer to any actually. So. The questions were, the first question was, if UDGs are peculiar galaxies, why can we apply relations between the globular cluster number and the halo mass, which this relation has inferred by local galaxies, in order to derive what the halo mass is? This is a very good question. We don't know if we can actually use the globular cluster number versus halo mass relation, but for most, I would say, if not all of the UDGs observed so far, the globular cluster number is what expected for galaxy of that particular stellar mass. And so we're a bit confident that perhaps the same relation apply, but it's a good question. Then someone asked me if we can, okay, in a paper by Mancera Pina, 2019, they found that observed field UDGs appear to have extremely low H1 gas velocity dispersion, about 4 kilometers per second. And is this compatible with our simulation prediction? I don't know. I didn't look at the gas of the H1 dispersion in our simulation. Just by eyes, it look extremely low, a dispersion of 4 kilometers per second. So I don't know if our simulation reproduces such a low one. I'll have to check. And then someone else asked if there is any observational confirmation that essentially the presence of cores is mass dependent. I would say, this is also a very good question, and I would say that yes, in the sense that most of, if not all, of the observational evidence for cores happen on a very specific mass range for galaxy between 10 to the 7, 10 to the 9. We do not observe any sign of cores for larger spiral galaxy or for smaller dwarf spheroidal, for example. It also must be said that in large galaxies, it's difficult to measure the inner dark matter content because they're baryon-dominated objects, so it's a bit, there is an extra complication. But if you're interested, you can go and have a look at a paper by Harley Katz, 2017, in which, am I allowed to show my screen, Fabio?
You still are, you should, I hope, try. Yeah, you're still, no, you're not a co-host anymore. I'm making you co-host right now. There you go.
Okay. Share screen. So this is a plot from a paper by Harley Katz. In this paper, what they did, they took rotation curve of about 200 galaxies, they are local galaxies from the SPARC dataset, and they fit these rotation curves using an NFW model in these two plots on the left, and a dark core mass dependent model here in the right side. And essentially what we were trying to show is that once you fit a model that predict cores to happen exactly in this mass range, 10 to the 7 to 10 to the 9 stellar masses, then all the results of your fit align nicely with expectation from lambda CDM. So you can take this as, you know, another point in favor of the fact that there is a core dependence in the real universe. I mean, after all, we never observed any signature of cores down here, and we never observe any signature of cores up here for large Milky Way or elliptical. We only ever observe signature of cores if you believe in those signatures, because, you know, after listening to Kyle's talk today, you may decide that you want to have a closer look at this rotation curve. But if you do believe in observational signatures, the only ones ever found are only in a very particular mass range.
Right. Thank you very much, Arianna. Is there, Julio, would you like to, is there anybody that I can see Julio has the camera on? I was assuming it meant he wanted to speak, but if not, I guess we have exhausted the questions that were asked during the day. There was a question to Jorge Almeda by Carlos, but that was asked during Jorge's session. So I guess, unless there are any further questions, we can thank all the speakers of this session once again. And we will reconvene in, I would say, 10 minutes for the speakers of the next session for the indirect in the gammas and photons, mostly. Okay, there is one quick question. Okay, Michael, go ahead, quick the question, but also please quick the answer. Michael, you want to speak directly? Probably
it's related actually to this last question, and I would ask it to Kyle, but if anybody else has an opinion, I'm really to listen. So is there any reason why you would expect that these observational effects lead to inference of cores only in this particular mass range of galaxies? Why don't rotation curves imply cores also in, okay, for higher masses, I guess is the point that Arianna already explained, but for example, in smaller galaxies, why don't we see cores?
Is a question for me, sorry, or for Kyle?
I think for Kyle, but if you have some opinion, I would be happy to hear it.
Yeah, well, I can comment quickly. Like one point, at least for massive galaxies, part of the answer is that for those, we typically have a much better handle on the geometry of the systems, right? So massive galaxies, I'm thinking of giant spirals where it's very clear that you have a circular disk and you can tell how it's oriented. Dwarf irregular galaxies still have probably a gas disk, but it's much harder to tell exactly what the geometry is, how thick is that disk, how is it inclined relative to us, so that causes problems. Very low mass galaxies, yeah, that I don't have a great answer for why we've never measured a core in those.
Well, if I may interject there, I mean, I think, if you take the data at face value, there are very low mass galaxies where there are apparently cores. It's just that the data is pretty ratty. As you go to very, very dwarf galaxies, they become very, very low surface brightness and the motions are really disturbed. So it's hard to know what is going on. But if you go to the paper by Santos that I was mentioning in my talk, you'll see some very, very faint galaxies where apparently there is a core. How much you believe it or not, that's a different question. But if you take data as published, then there are galaxies there.
What stellar masses we talking about, Julio, for this galaxy?
10 to the 6, 10 to the 7, so a very low mass, well in the regime that at least in your models, in your simulations, you find no cores.
No, I think in our simulation and in pretty much, well, in every simulation where they find cores, they start finding cores at around 10 to the 6. That's the starting point. Of course, it depends on your definition of core. It's not just a flat profile, it's just a little bit, flatter compared to the NFW model. From an energetic point of view, it makes sense that it's difficult to form cores. I was thinking about ultra faint, right? If you have a galaxy of 10 to the 4 stellar, then you just don't have many stars. So the energetic contribution from your supernova is not that large. But I think if we want to really start looking into these a little bit, trying to look at that at the scale of stellar and see what we find. If we find cores below that scale, then it's really difficult from baryonic physics to find that.
Mm-hmm.
Okay, thank you very much.
Thank you, Michael, for the question. And again, let's thank all the speakers of the session again and of the previous session. And we can reconvene in 8 minutes for those of you who are going to speak in the next session. So Miguel Sanchez Conde, Javier Coronado Vázquez, Anastasia Sokolenko, Elena Pinetti, Ayon Diana, y Alfonso Jorge. Please be here in 8 to 9 minutes. And in the meantime, don't forget to entertain yourself with Brazilian music. I'll see